Hello students, good evening. Welcome to HashLearn, and today we are dealing with a chapter called as Electromagnetic Induction. We have come to the most important class. Or today's topic is self and mutual inductance. We are discussing the concept called as self and mutual inductance, which is very important from the exam point of view. So any exam point of view in general. So we will be learning with that self and mutual inductance in the in the detailed manner. So with this I think we are good to start. Anyways, it's a Saturday night, Shaniwar ke raat, Sri Harsha sir ke saath. So we will be learning on the concept of self and mutual inductance. So we are starting with today's concepts of self and mutual inductance. So the recap of the previous classes is, as we had discussed about the electromotive force, or in general it was conservation of energy from mechanical energy to electrical energy. So we had taken an example of the magnetic field which is acting inwards. हमारे पास एक मैग्नेटिक फील्ड है जो अंदर की तरफ जा रहा है, उस पे एक कंडक्टिंग रॉड है, उसका लेंथ L है. सो दिस इज द लेंथ ऑफ द रॉड, उसका लेंथ L है, एंड ए तो मैग्नेटिक फील्ड का डायरेक्शन है. सो दिस वी आर कैलकुलेटिंग द EMF इंड्यूस्ड ड्यू टू दिस. यहां पे क्या होगा कि हम यहां पे एक अजम्पशन ले रहे हैं कि ये जो कंडक्टिंग रॉड है वो इस तरफ जाएगा विद द वेलोसिटी v. In the initial condition, so the flux is equal to 0 because it is equal to at rest. अगर एक थोड़ा सा डिस्टेंस dx जाएगा तो उसका फ्लक्स 2 होगा b into L into dx, where L into dx is the area. As simple as that. और उसके हिसाब से हमारा मैग्नेटिक फील्ड की अंदर की तरफ जा रहा है और वेलोसिटी परपेंडिकुलर है, सो तो थीटा होगा 90 डिग्रीज. सो विच वी ऑल नो दैट. सो द मैग्नेटिक फील्ड एंड द थीटा इज एरिया तो इस तरफ है, वेलोसिटी इस तरफ है और मैग्नेटिक फील्ड इस तरफ है. सो द एरिया एंड द एंगल बिटवीन द एरिया एंड द मैग्नेटिक फील्ड इज 0 डिग्रीज. सो द cos 0 इज इक्वल टू 1. सो इसके हिसाब से E इक्वल्स phi2 minus phi1 by t which is equal to BL dx by dt, where dt is the time. So इसके हिसाब से the induced EMF is given by BLV. So the direction is the forefinger in the terms of magnetic field, and the thumb giving the direction of the velocity, and this is the direction of the induced EMF. Hi Peru, very good evening, welcome on board. So on the weekend you are here, that's nice. So that's the commitment. I want others to have the same commitment through. So this is the emotional EMF. इसके अलावा हमने दूसरा कंडीशन पे बात किया था, जब if we have a magnetic field in the same particular direction, and let us assume you have a conducting rod of length L which is making a circle. So which is making a circle, then the EMF is given by E equals half BLV. ड्यू टू द रोटेशन इसका इंड्यूस्ड EMF होगा हाफ BLV, विच वॉज ऑल्सो गिवन बाय ही इक्वल्स हाफ BL स्क्वायर ओमेगा, वेयर ओमेगा इज इन टर्म्स ऑफ एंगुलर वेलोसिटी और V is in terms of linear velocity. So with that we have come to the recap of the previous classes. We solved few problems based on this. Now before we start, we have the two long conductors separated by a distance d. They exert force on each other, and the current is one of them is reversed and its direction is reversed. The distance is also increased to 3d. What is the new value of force between them? So this is the answer is equal to option C, which is the problem taken from the concept of magnetic field, taken from the magnetic field due to a conductor. So it was from the moving charges and magnetism. So the answer is C. So that was the most important CPP from the last class. So now we have the next. So today's concept is called as the self and mutual inductance. So before we start with the self and mutual inductance, students, so we have to know certain concepts of first year or class 11th, which is very important to us. So the first thing, what is actually inductance? So inductance क्या होता है और ये किसके रूप में होता है, वी आर स्टडीइंग ऑन दैट. सो व्हाट इज एक्चुअली इंडक्टेंस or what is it all about? So the first thing over here is, we will take a simple example. The first thing over here is, let us assume I have a coil. So I have a coil and this coil has n number of turns, and this is connected to a battery via a plug key or a switch. So let us assume there are n number of turns in this complete coil. अगर मैं बैटरी स्विच ऑन करके इस प्लग की को क्लोज करूं, सो हमें पता है कि द करंट इंक्रीजेस फ्रॉम 0 to t in a certain value, where I is the maximum current and 0 is the minimum current. जब हम उसको प्लॉट करेंगे, when I plot the current versus time, what we expect is the current instantaneously becomes from 0 to I. So it is as simple as expecting, हम जब बैटरी ऑफ था करंट वाज 0, when I switch on the battery the current should be I. But what I see, if I start plotting the graph, I see that there is a gradual rise in the current. So it is not happening instantaneously, it is taking a finite amount of time. So when it is making a finite amount of time, there has to be a certain reason. So the reason what is actually opening over here is, what is happening over here is, now let us assume I have some beautiful slow motion recording camera which is gonna measure the current in a very, very slow motion way. So now first, as soon as I close the plug key, you see that the current starts from the battery. When it reaches the first coil, it makes one complete turn and then reaches the second coil. So when it has made one complete circle in the first coil, we know from the right hand class it is inducing a magnetic field. So it is inducing a magnetic field, and that induced magnetic field will create a change in flux. And whenever there is a change in flux, we know that there is an opposing EMF induced. और EMF इंड्यूस का जो काम है, उसका काम है फ्लक्स को जो चेंज कर रहा है उसको अपोज करना. एंड द ओनली थिंग विच इज चेंजिंग द फ्लक्स ओवर हियर इज द चेंज इन द करंट. सो व्हेन द करंट इज चेंजिंग, देयर इज अ फ्लक्स इंड्यूस्ड इन द कॉइल विच अपोजेस द ग्रोथ ऑफ करंट, सो इसीलिए वो थोड़ा वक्त लेता है. And that property of the coil which opposes the growth or the decay of current in general is called as inductance. So inductance is that property which opposes any change in current. So inductance is a property of the circuit. Inductance is the property of the circuit which opposes the current in the circuit, So this is called as the inductance. And if you are familiar with this, students, we had studied the same concept in class 11 in a different context. So, or if I compare this to the mechanics and physics, it is also called as, the inductance is also called as electrical inertia. It is also called as electrical inertia. So inertia ka kya, what is the job of inertia? To oppose the cause acting on the force. If I impose a force, it wouldn't start suddenly moving it. It will oppose that force, and that is called as inertia, which we are very familiar. So which is, the inductance is also called as electrical inertia. Now the first thing what we are learning over here in this class is called as the self-inductance, and I hope you are very familiar or you have understood the definition of inductance. It is the property of the circuit which opposes the current in the circuit. So let us take, you have a coil and it is connected to a battery and a plug key. So it has n number of turns and the current is I. So the flux induced is directly proportional to the change in current. The number of turns times the flux is directly proportional to current. We know that when the current is increasing, हमें पता है magnetic field is directly proportional to current. When the current is increasing, then the magnetic field is also increasing. When the magnetic field is increasing, then the flux will also increase. So this I can directly write it as flux is directly proportional to the current. So we have it as N phi is equal to L into I, where L is the constant of proportionality called as self-inductance. So L is the constant of proportionality, where L is the constant of proportionality and it is called as self-inductance. So it is the constant of proportionality which is called as the self-inductance, which is actually defined as, so if I is equal to 1 ampere and number of turns is equal to 1 turn, then L is equal to phi. So the self-inductance is equal to the flux induced in the coil of 1 turn with 1 ampere. So with this you can also write it as the induced EMF is given by minus d phi by dt, which is equal to E times minus d by dt of n phi is equal to Li. So if you take for n turns, so L into I, which is equal to minus L times di by dt. So the EMF induced is equal to di by dt. So this is very, very, very important expression for the induced EMF. So the induced EMF is given by E equals minus L times di by dt. So from this we can define E is equal to minus L times di by dt if di by dt is equal to 1 ampere per second, then L is equal to minus E. The self-inductance is defined as the opposing EMF in a coil when the change in the current in the same coil is 1 ampere per second. The self-inductance is defined as the opposing EMF induced in the coil when the current in the same coil is changing at the rate of 1 ampere per second. So that is your self-inductance, which is equal to L into di by dt. So now the SI unit is the self-inductance is expressed in the unit called as Henry. So it is called as Henry is the SI unit of the self-inductance. The self-inductance depends on, the first one is number of turns, the magnetic field, and the delta I as well as delta T. So it is number of turns, the magnetic field value, the change in the current, and the change in the time interval. So these are the factors on which the self-inductance depends on. The self-inductance is said to be 1 Henry if 1 volt of EMF is induced. 1 volt of EMF induced when the rate of change of current is 1 ampere per second. The self-inductance is said to be 1 Henry if 1 volt of EMF is induced when the rate of change of current is 1 ampere per second. So now let us assume you have, so we are dealing, the next concept is called as the energy stored in the coil. So the energy stored in the coil. So let us assume you have a coil again with n number of turns connected to a battery. So the work done in dissipating the charge is dW equals LIDI. The work done is given by LIDI, where L is the self-inductance, I is the current. So to find the total energy, you integrate it from 0 to LIDI. So that will be equal to L is constant, so 0 to I di. So you integrate this, you get it as I square by 2. So this the energy stored is half Li square, which is very similar to U equals half CV square, which we studied in the capacitor. The only difference is in capacitor the form is of electrostatic energy. Electrostatic energy. Whereas here it is in the form of magnetic energy. Here it is in the form of magnetic energy. So that is the only difference. So you can see that the total work done in that half is stored as energy and the remaining half is dissipated as heat. So that is the expression. So now you have the first thing what we are calculating over here is how do we calculate the self-inductance. So how to calculate the self-inductance? How to calculate the L? I am giving the general formula. We have it as N phi is equal to L into I, or L is equal to N phi by I, which is equal to NBA cos theta by I. So that gives the value of the self-inductance. So if theta is equal to 0, then L is equal to NBA by I is the self-inductance formula. Or you can also write for the due to the coil B equals mu naught Ni. So if you remember from the solenoid, the magnetic field is given by mu naught Ni, then N is equal to mu naught Ni by I, which gets cancelled. So I gets cancelled, so into area, so mu naught N square A. So if you take the area as pi r square, then you'll have the expression. So that is your N into L, sorry, L in mu naught N square L into A. So that is the self-inductance in terms of the magnetic field. So now we have the next concept of today's class, and that is called as mutual inductance. So mutual inductance and the self-inductance is almost the same, with the small changes that self-inductance is the same coil, whereas the mutual inductance is because of the two different coils. Self-inductance is because of the same coil, whereas the mutual inductance is because of the different coils. Now let us say you have one coil, this is connected to the galvanometer, and you have another coil which is connected to the battery and a plug key. So this is called as the secondary coil, and the current and the coil in which the current is moving, it is called as the primary coil. Now let us say this has N2 number of turns and this has N1 number of turns. So whenever there is a change in the current coil, we know that when I close the switch and I say the current is moving, so in the coil when the current is moving, there is a magnetic field induced. There is a magnetic field induced in this direction. So whenever there is a magnetic field induced, there is a change in flux in the secondary coil, due to which there is a current induced, which we have studied in the coil and coil galvanometer. But this change in flux will give rise to the change in the induced EMF. So you will have it as N1, if you have talk about the number of turns, so you have the number of turns as N1 and N2. So you will have it as, let us take the general condition where you have it as N2 phi 2 is proportional to I1, where the current is in the primary coil I1. So this so this can be written as N2 phi 2 is equal to M times I1, or M is equal to N2 phi 2 by I1. So where if I1 is equal, or in general, M is equal to N phi by I. In general, the magnetic flux is equal to N phi by I, where N is number of turns and flux is the, phi is the flux and I is the current. So with this we can say M is equal to the flux induced when I is equal to 1 ampere and the number of turns is equal to 1. So this is very similar to the self-inductance, but the difference is the current is moving in the one coil and the current is, the EMF, there is an opposing or the induced EMF opposing the growth of the current in that coil. So now we have the expression for induced EMF, which is equal to minus N times d phi by dt, which is equal to minus M times di by dt, or this, the magnitude of the induced EMF is equal to M times di by dt. So if di by dt is equal to 1 ampere per second, then the induced EMF is equal to the mutual inductance. The mutual inductance is numerically equal to the induced EMF in the secondary coil when there is a change in the current in the primary coil at the rate of 1 ampere per second. So listen to these words carefully. Mutual inductance is equal to the EMF induced in the coil, secondary coil, when the current changes at the rate of 1 ampere per second in the primary coil. So that is called as the mutual inductance, and if the EMF induced is equal to 1 volt, then mutual inductance is equal to 1 Henry. The mutual inductance is said to be equal to 1 Henry if the EMF induced in one coil is equal to the 1 volt in the secondary coil when the current in the primary coil changes at the rate of 1 ampere per second. So that was the mutual inductance. Now how do we calculate, or what are the factors it depends on? It depends on number of turns like the previous case, length, area of cross section, and the magnetic field. So we have, let us assume, let us assume you have two coils. So this is N2 and you have another coil which has N1. So you will have it as N2 phi 2 is equal to M times I1. So N2 phi 2 is equal to M times I1, where flux 2 is equal to B1 times A. Assuming both have the same area of cross section. Assuming both are having the same area of cross section, so you will have it as, so you can write this as N2 B1A divided by I1 will give you the mutual inductance, or N2 times mu naught N1, capital N1 A divided by L times I1, which I gets cancelled. So I1 will get cancelled. So you will have it as the mutual inductance is mu naught N1 N2 A by L. So this is the general expression for the coil, assuming the coils are of solenoid. There is one factor on which the coil, the mutual inductance depends on. So the mutual inductance depends on the one coil which is called as the coupling constant. So if they are tightly coupled, so which means one coil is something like this and the other coil is something like this, then the value of the mutual inductance is given by root of L1 L2, where L1 and L2 are the self inductances. Then you will have it, that is the first condition. Then you will have it as, then this is called as loosely coupled, one coil and the other coil. So here the coupling constant is less than 1. This is called as coupling constant, and if one coil is like this and the other coil is like this, then the coupling constant is 0. So this has to be remembered. And if you have two coils connected in series, then the effective self-inductance is given by L1 plus L2, same like your resistors in series. And then, so if you have them connected in parallel, then you will have it as L effective is equal to L1 L2 by L1 plus L2. So with this, students, we have come to the end of the synopsis. Now we have the first problem on the screen for you. So we have the first problem on the screen. A circular coil of radius 5 cm has 500 turns of a wire. The approximate value of coefficient of the self-inductance will be equal to 25 millihenry, 25 to 10 power minus 3 millihenry or 15 to 10 power minus 34 millihenry, or the 50 into 10 power minus 3 Henry. Come on students, give me the correct answer. Come on Peru, answer up. Right, so for a circular coil, remember this students, for the self-inductance of a circular coil is given by pi times mu naught n square r by 2. So this you have to remember, the length, the self-inductance of the circular coil is given by pi times mu naught n square r by 2. So if you substitute the values, you will have it as pi into 4 pi into 10 power minus 7 500 square, and the radius is 0.5 square divided by 2. So if you solve this, you'll get the answer as 25 millihenry. So the self-inductance of the circular coil is given by pi times mu naught n square r by 2. That is the length, that is the self-inductance of the circular coil. So you substitute the values and simplify it. It is a normal basic mathematics simplification, students. So that will be equal to 25 millihenry. So now we have the next problem on your screen. A solenoid has a 200 turns wound over a length of 0.3 meter. The area of its cross section is 1.2 into 10 power minus 3 meter square. Around its central section, a coil of 200 turns. A coil of 300 turns is wound, and initial current of 2 ampere in the solenoid is reversed in 0.25 seconds. Calculate the EMF induced. So this was done asked in 1982. 6 into 10 power minus 4 volts, 4 into 10 power minus 3 volts, 6 into 10 power minus 2 volts, or 48 millivolts. So what is the correct answer? So there are two coils over here, so you think properly what has to be used. Come on students, I'm waiting for your answer. So the first thing we have to calculate over here is the mutual inductance, because you have two coils. So the mutual inductance is given by the formula mu naught N1 N2A by L, where the length is equal to how much? 300 meters. So if you solve this, you'll get it as 4 pi into 10 power minus 7 into 2000 into number of turns is 300, and pi r, the area of cross section is given as 1.2 into 10 power minus 3 divided by 0.3. You get the mutual inductance as 3 into 10 power minus 3 Henry. So the mutual inductance will be 3 Henry, and the magnitude of the EMF is given by m times di by dt. On solving, you will have it as 3 into 10 power minus 3 into reversing the current, so minus of minus 2 in 0.25 seconds. So you'll get the answer as 48 millivolts. So this is the answer, 48 millivolts. So we are using two concepts over here. First, you are finding the mutual inductance and then the EMF induced by it. So I hope you are clear with this, students. So now we have the next problem on the screen. The coefficient of a self-inductance of a solenoid is 0.1. If a core of soft iron of relative permeability 900 is inserted, then the coefficient of self-inductance will nearly become equal to how much? This is very simple problem, students. I think you need to solve within 30 seconds. You can solve it out. Come on, students, I'm waiting for your answer. So we know that the self-inductance of a coil is given by the formula L equals, so L equals mu naught N square A by L, or the length. If I introduce some other medium, you will have it as mu naught mu R N square A by L. So that is equal to L medium, this is in air, so you'll have it as mu R into L air. So mu R value is 900 and the self-inductance is 0.18 millihenry. If you solve this, you get it as 18 into 9, which is equal to 180, that is 162 millihenry. So the answer is 162 millihenry, students. That is the option B. So I think you have understood this problem. Now we have the next problem. Oh my God, Teru, you responded. That's so nice. So now we have the next problem on your screen. If the current in the inductor is given by I equals 2 plus 3t ampere, where t is in the seconds, the self-inductance and it is 9 millivolts, and the energy stored in the inductor at t equals 1 second is. We have to find out the energy stored at t equals 1 second. 1 second. Come on, students, you can solve it. This is very, 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 very easy. Come on, students. So the first thing, let us know the current at 1 second. I at t equals 1 second will be 2 plus 3, which is equal to 5 ampere. Here E is equal to 9 millivolts. We know that E is equal to L into di by dt if I take the magnitude. So 9 into 10 power minus 3 is equal to L into d by dt of 2 plus 3t. If you differentiate this, you will get it as L into 3. So L is equal to 3 millihenry. The energy stored is half into Li square, which is half into 3 into 10 power minus 3 into 25. So with this, you will have it as 75 milli divided by 2, that is joules, which is equal to 37.5 millijoules. So the correct answer is B. This was a very nice problem, students. So where they have given in a tricky way, but it is a very simple one. The number of turns in two coils A and B are 300 and 400 respectively. They are placed close to each other. The coefficient of mutual inductance between them is 24 millihenry. If the current passing through the coil A is 2 ampere, then the flux linkage in the coil B will be equal to how much? This is again a very simple problem, students. What is the flux induced in the secondary coil due to the change in the current in the primary coil? Come on students, I'm waiting for your answer. Right students, so we have the flux linkage is given by N2 phi 2 is equal to M times I1. So that is equal to M value is how much? 24. So N2 phi 2 will be equal to 24 into 10 power minus 3 into 2, which is equal to 48 into 10 power minus 3, which is 48 milliweber. So the correct answer is C. So the 48 milliweber is the answer students. So before we continue with the problems, we have the previous class contest question. The flux for the induced EMF in a coil due to the change in the magnetic flux through a coil is given by, the correct answer is Y, and the lucky winner to win the atom session is Peru. Congratulations Peru, clap clap clap. So you have won one atom session. So students, so in every class we have something called as contest question, and the person who answers it correctly in the short interval of time wins an atom session. With that, he or she can get one doubt clarified for absolutely free of cost. Now we have the today's contest question on your screen. The today's contest question is on the screen as shown. So that's the Peru is the lucky winner. So now we have the contest time is solenoid is 1.5 meter long and its inner diameter is 4 centimeter. It has 3 layers of winding of 1000 turns each and carries a current of 2 amperes. The magnetic flux for a cross section of the solenoid is nearly equal to how much? 2.5 into 10 power minus 7 Weber, 6.31, 5.2 or 4.1. So today's contest question, we have an announcement. The winner along with the correct answer will be announced in the next physics class students. So I am hoping to see the winner. Now we have the next problem. A coil of wire of certain radius has 600 turns and a self-inductance of 108. What is the self-inductance of the another similar coil of 500 turns will be? This was asked in the year Madhya Pradesh PMT 1990. Come on students, I'm waiting for your answer. So we know that L is equal to mu naught N square A by L. As the coils are similar, L is proportional to N square. So L1 by L2 is equal to N1 by N2 the whole square. So L1 is 108, L2 is unknown, N1 is 600 by 500 whole square. So this gets cancelled. So you'll have it as 108 by L2 is equal to 36 by 25. So the nearest multiples of this is 12 times and this is 36 times and this is thrice. So L2 is equal to 75 millihenry. So the correct answer is B. So now we have the next problem on the screen. So two different coils have self-inductance L1 and L2. equals 8 millihenry and 2 millihenry. The current in the coil is increased at the constant rate. The current in the secondary coil is also increased at this constant rate. At a certain instant of time, the power of the given two coils will remain the same. At what time the current, induced voltage and the coils are I1, V1 and W1 respectively. The corresponding at the second coil is I2, V2 respectively. Then choose the correct option. So you will have it as I1 by I2 is equal to 1 by 4, or I1 by I2 is equal to 4. W2 by W1 is equal to 4, or V1 by V2 is equal to 1 by 4. So which is the correct answer? So with this, students, we have the first one is E1 by E2 is equal to L1 by L2 because di by dt is same. So with this, you will have it as E1 by E2 is equal to 8 by 2, which is equal to 4. So that is V2 by V1 will be equal to 1 by 4. Sorry, that is the correct answer is V2 by V1. So V2 by V1 will be equal to, or V1 by V2 is equal to 4. So this is the correct answer. So this cannot be taken. So we know that the power is given by V into I, or we can say I is proportional to V. So I1 by I2 will be equal to V2 by V1, which is equal to L1 by L2. So what this, you will have it as I1 by I2 is equal to V2 by V1, which is equal to how much? So V2 by V1 will be reciprocal of this, which is equal to 1 by 4. So I1 by I2 is also the correct answer. So it is evidently visible that the correct, so this is the wrong option. So the correct answer is B. So because we have got the value as I1 by I2 as 1 by 4, so I1 by I2 cannot be equal to 4:1. So with this, students, we have come to the today's class. So we have the summary of the today's class. We dealt with the self and the mutual inductance, which is also called as electrical inertia. It is called as the electrical inertia, so which is represented as L and M. So self-inductance and the mutual inductance. So thank you for joining us, students. I hope you have liked this class. If you have liked them, please do share this video among all your friends. Now with CPP time, it is available for the passport members. We have given the 10 best questions from the topic discussed today. It is unlocked and available for the passport members. For non-passport members, CPP is locked, and to unlock you need to subscribe to passport. If you subscribe to passport, you also get access to 24/7 1-to-1 doubt solving, practice questions in the test from the best selling books, and all the videos covering the toughest concept. With this, students, I take a leave from you. Happy weekend, good night, and passport members, please don't go anywhere. Now it's your CPP time. All the best, good luck, good night, happy weekend, sayonara.